Hi, good afternoon, everybody. I just wanted to start by saying I'm really sorry that I can't be live on video presenting today like I was yesterday. I had a family emergency come up, and where I am right now, right now when I'm talking to you, not right now when I'm recording this. It's actually late last night when I'm recording this, but right now where I am, it doesn't have very good service, and so I really couldn't guarantee that this was going to work very well for my computer. So I wanted to pre-record it. And if service is good enough, I will try to join on the chat for parts of it, or maybe even with audio to try to answer some questions. But I wanted to make sure I pre-record this so you have really good video walkthrough here. And I know that with Marco and Marcelo and others, you're in very good hands in the room. And again, I'm really sorry about the crazy last minute family emergency thing. So with that said, today, I'm going to be talking about data pre-processing for hands-on keyword spotting. And what that means is, first, I want to give you that quick disclaimer again, that things are probably going to be too fast and too slow because, as I said yesterday, we have a varied group here of different kinds of skill levels. And based on the survey feedback from yesterday, and thank you to those of you who did fill out the survey, most people thought that the content was pretty good, right? There's about as many people that thought it was too high level as people who thought it was too detailed. So that to me says I'm probably doing the right thing, kind of hitting it right in the middle there for all of you. So I would expect this to be at a similar level of detail. It seems like though some people thought it was a little bit too fast. And so I'll try to be a tad slower, but I don't want to go too slow because most people thought it was just right. The one other comment that came up a bunch in the free text response was, please add more information about how to use your cell phone. So I will include a little bit more of some screenshots about how to use a cell phone there. And I just want to remind you that this video recording, these slides are all posted on the website already. And I'm working on all the rest of the video recordings, and I will get everything posted as soon as I can. Just working through a little bit of personal chaos this week. So keyword spotting in one slide. What are we doing today? We are going to take a relatively simple task compared to we're not translating the world. We're not creating Siri to understand and know everything. What we're doing is we're trying to identify a few keywords, which will allow us to use a small model, train it with very little data, and fit it onto an embedded device. And the kind of model we're trying to train is just the model that understands, okay, Google, hey Alexa, hey Siri. I'm sure I lit up a bunch of your phones. I'm sorry. But the basic commands there. And in this case today, we're going to just do yes and no, or you can do your own custom keywords if you'd like. I've gotten yes and no to work, so that's sort of what I did. But you can sort of do whatever you want. Probably 2 keywords again, and we're going to walk through a little bit of the theory behind it and then do the practice. Yeah, so we'll do a little bit of the science, and then we will deploy it on Edge Impulse. So I wanted to start first, though, by doing a quick review of what we've learned throughout this workshop and what we talked about yesterday, because this is going to build on what we learned yesterday. So if you remember, we've talked a lot about machine learning. We've talked about how we need to label some data, provide some answers of what we want the model to understand, and then the computer will learn the rules to that model. We've talked a lot about using neural networks and how they're pretty good at taking a high-dimensional input data and figuring out how to classify it into different classes. We talked about how convolutions are really good ways to find features in images. And we also talked about how convolutional neural networks leverage that feature finding ability of convolutions and automate the process to find the best possible features for the computer, and then use that to actually classify to figure out how to actually solve the problem that we want. We also talked about the whole TinyML workflow, and we sort of worked through collecting data, pre-processing, designing, training a model, optimizing our model with some quantization, and deploying it onto a device. And we did that in Edge Impulse through their dataset impulse test deploy sort of framework. And yesterday we did vision. Today we're doing audio, although spoiler alert, it turns out that the best way to do audio is actually to pre-process it into basically a vision problem. So we'll be using those convolutional neural networks again, and I'll get into why that is the case and sort of what that pre-processing is in the next bit of this presentation. So before we go through a little bit of the theory and actually do the training, first I want to talk a little bit about actually collecting data. Because I think one thing that you might be realizing, or one thing that I think Vijay was harping on a lot in his keynote, was that the problem here is a data problem often, right? It's hard to collect the data. And actually we saw that in some of the case studies yesterday. The challenge is going out into the field and collecting the data so that we can then do some training. And so if the hard part is collecting the data, we should think carefully about what data we want to collect and how we want to collect it so that once we get it, we have good high quality data that we can use in our projects. So I'm going to talk a little bit about data engineering for keyword spotting, but also we'll point out sort of how to collect good data in general. In general, there's three big questions that you want to think about. The first is, who will use your machine learning model? In the case of audio language or keyword spotting, we want to understand what languages, what sort of accents, what sort of slang people are using, so that we pick relevant keywords and we collect data that captures the diversity of the kinds of speakers that are going to be using our product. The second big question we want to answer is, where will our model be used? We want to think about things like background noise, distance to the microphone, echoes, all these sorts of things in the environment that will affect how well our model works. You can imagine in the case of different kinds of sensors, you would care about different kinds of interference from the environment. But in general, if you're not going out and including in your training set things about the real environment, if you record audio in a studio, in a music studio, in a perfectly soundproof music studio, and then you try to deploy your model in the real world where there's all this background noise, it likely won't work. The third thing you want to think about is, why will your model be used? Or why those keywords in this case? So this sort of gets into false positives, false negatives, and tonality of users. Because even if you account for languages and accents and slangs, if somebody is very stressed and they're screaming the keywords at the system versus saying them normally, that will actually create a very different audio signal. And so you need to understand the use cases for it, and you need to understand what happens if you get a false positive or a false negative. So like, what happens if your model doesn't trigger? If it's just keyword spotting on your phone, right? If you ask your phone, hey, whatever, and it doesn't work, you say it again, and it's not a big deal. So it's really kind of okay if it's wrong, and occasionally your phone seems to just like wake up and listen to you, and it's annoying, but it's not a big deal. So again, sort of false positives aren't that problematic. But you can imagine if you have a system that has to deal with, human health or burglar detection or unlocking doors. Suddenly now false positives and false negatives become really important and can become critical. And so you need to understand sort of how much data do you need around things that might trick it up, right? If your keyword, if you were using it as like a password and your keyword was, hello, you might want to also train it with like mellow to make sure that somebody doesn't get close to the right word and then unlock your secret safe or whatnot. So that's just a little bit of high level on data engineering. And there's a lot more things to consider here because we also have to think about bias and privacy, right? You can't just go around collecting random people's audio signals and using them without their permission. You have to worry about if you only collect from certain groups of people, you're going to introduce a lot of bias into your system such that it won't work for others. For example, there's been a lot of papers that have shown that a lot of early machine learning models were mainly trained on people with lighter skin tones and mainly on males. And so if you had females or people with darker complexions, these sort of like face recognition models were failing. And so it's very important that we think about who's in the data set, what's in the data set, who are our users, so we can get something that's actually useful for people and doesn't leave some people behind unnecessarily. And I know Susan will talk later today a lot more about some of the ethics around TinyML. So in general, if you're doing keyword spotting and you want to actually deploy something, you're going to want to pick uncommon words that won't likely accidentally cause false positives. You'll want to record a lot of other words that are distractor words so that your model can learn just your keywords and not English in general. You're going to want to record in the location you're going to be deploying. You want to get your end users to help build your data set, or at least get representative users to build that data set and record with the same hardware you will deploy with so that there isn't like a difference in microphones. We talked about this a little bit yesterday. If you take pictures on your computer and then deploy it onto the Arduino, the camera is different. And in fact, the microphone is also going to be different. And that might cause some problems. And then always test and improve your model after you deploy it. But for today, we're going to cheat. We're going to try to do something that works again to make sure we get something that you can build on in the future. So I would suggest that when you are recording, you only record yourself or the group of you that are in the room if you're working together. You use very common words that'll be easy and short and simple and sound different, like yes and no, right? Different vowels, different consonants will make it easier for the computer to tell them apart. You only test on yourself because you only trained on yourself, and you stay in one spot, and wherever you record, you test exactly there. Cheating, but good suggestions for getting something to work today. So what we're going to do then with sort of that in mind is I'd like you to think about 2 keywords that you might like to do, and we're going to actually record them with Edge Impulse, just like we did yesterday. So we're going to work through that data set step. And again, if you don't have an Edge Impulse account now, great one, studio.edgeimpulse.com/signup, or log into your Edge Impulse account. We're actually not going to just create a new project. What we're going to do is actually clone a project that I have, but let me just first say what our activity is going to be, and then I'll walk you through the steps because I just want you to understand where we're going. So we're going to want to record about 30 to 50 samples, and if you can get up to 50, it'll probably work better, of 2 keywords. Maybe yes and no is sort of my suggestion. And in theory, we also want to record some unknown words that are not keywords and some background noise and static and some other things to help the model understand what is your keywords and what is just noise in the environment and language in general. But I've preloaded a bunch of background noise and unknown words into a project that you can clone, which will save you the trouble of having to do that. And it's based on Edge Impulse's pre-built example for yes and no, except for I stripped out all the yeses and nos so that you can supply your own keywords or your own recording of those keywords. But it's all there static and noise. The link is on the top right if you want to see their full data set. But for today, what you can do is you can actually go to this link, bit.ly, bit.ly/SciTinyML22-KWS for keyword spotting. And if you go to that link, you will get to my project here. And it should just be the SciTinyML22 keyword spotting project under Harvard. And up at the top, there's this black bar, and you can click clone this project, which will bring up this pop-up where you want to click clone. And you may get the developer or enterprise option. I get it, I know, because I'm part of like the Harvard organization. I don't know if you will get that option. If you don't worry about it. We're using the developer or like the free version anyway, so just click clone there. But the link you want to go to is bit.ly/SciTinyML22-keyword spotting. And since this is pre-recorded, I'm just going to pause for a moment and leave it on the screen. And this might be a good moment for any sort of questions or anything people have so far. So not pausing for too long in case somebody actually hit pause and then you get stuck with silence for a while. But if you're still asking questions or you still want more, pause me. I'm going to keep going. I'm going to assume you cloned that project, and it might take a little while for the clone to happen. You're going to get another one of those sort of things where it's restoring a bunch of files, and this could take a little bit of time. This could take a couple of minutes because I'm loading in 3,000 or so files into the browser for you. But this will save you the trouble of having to record that data and having to maybe download and upload. So hopefully that'll save you on some data usage as well, since this is all happening. So we're going to go to data acquisition, and we're going to acquire some of our own custom data. And remember, again, I've preloaded in here. So when you go there, you will already see things. There's 50 minutes of data in there. A lot of them are noise or unknown words. And you can click on them and listen to them if you'd like to. But per the feedback from yesterday in terms of can we get more of the phone instructions too, as well as the Tiny Machine Learning Kit instructions, I'm going to first show you quickly what you would do if you're just using a cell phone, and then I'll talk through how you can go about recording the data on your Arduino. And I grabbed this slide from the ethics course because I wanted to point out that The phone and the Arduino are actually relatively similar in terms of kind of the sensors that you have in there. It's just that the phone has much nicer sensors, much more expensive sensors, and the phone is probably much more expensive than the Arduino. But we have a camera, we have accelerometers, we have microphones, and we have compute. So it's kind of cool, I think, actually, when you put them side by side, they look nice. So if you want to use your phone, there should be a pop-up sort of across the top that says, did you know you can capture data from any device? And you can click show options. And what that'll do is that will pull up this thing that says, how would you like to collect data? And this is where, as I said yesterday, if you click show QR code, it will give you a QR code that if you pull up your phone camera and you point it at the QR code, it should bring you to a link. And I'll show you where that brings you in a second. And that will let you start recording on your phone. If you have a computer that's not being used for this Zoom and you'd like to record on the computer, you can do a similar sort of thing by clicking collect data, and it will actually try to record directly on the computer that you're using. Yeah, point your phone at the QR code and open the link. So when you open the link, you will get, this thing will show up on your phone. It will say connected as phone something or other. And so you can then click on collecting audio because we're doing audio samples today. And then you'll get to sort of this screen where you get label, length, and category. And so if you click on label, that will bring up a text box where you can sort of enter whatever label you want. So this is yes and no, or this is whatever it is, but you enter the one word that you're currently recording. And then what you can do is you can also change the length. And so if you're recording one recording of one word, you might want to do it at 1 second, but I'm going to show you actually, after we talk through how you do it on the phone, that we can actually record like 10 or 20 seconds of data, and then we can use that tools inside of Edge Impulse to allow us to split that into all the 1 second chunks that we actually want. And then category, you can do to training or test or split, and it'll automatically split it. We're going to still automatically split all the data later. So for now, it actually doesn't really matter what you do there. And if you want more information on how to use your phone with Edge Impulse, there's good documentation from Edge Impulse down at the link here, docs.edgeimpulse.com/docs/using your mobile phone. Or if you Google Edge Impulse using mobile phone, it should bring you to the same page. So hopefully that helps you if you're using your phone. If you're using your Arduino Tiny Machine Learning Kit, we're going to do the same thing we did yesterday. We're going to click connect using web USB. And again, remember, if you have a failure to connect, what's going on is that likely you need to reflash the Edge Impulse firmware. And so as from before, you can go to bit.ly/ei-nano33-firmware, and that will download the firmware, but you may already have it on your computer from yesterday unless you deleted it. And so you can just run Flash Windows, Flash Mac, or Flash Linux, depending on what you are using. So again, once you've reflashed that firmware, and I will bring that link back up later, you can then go and just pair your Nano 33, and then we'll get back to that recording page like before. And as with yesterday, there's a couple of drop downs that you can pick. Since this already has some audio built into this project, it should automatically select the built-in microphone here and the correct 1600 hertz or 16,000 hertz. So all you need to change is the label and the sample length. And here's where actually I started recording 10-second clips, which is like 10,000 milliseconds for my label, just so I could say the word a bunch of times. Because once you click start sampling, it takes a little bit of time for it to connect to the Arduino and get going. And so I wanted to just amortize that process. And so once you click start sampling, it'll go along and you'll end up with a clip like up here in the top left, yes, dot some number, and it's 10 seconds versus all these other ones are only 1 second. And if you record on your phone, they will also end up coming into here. And so once you're done with all your recordings, we'll need to actually split these into 1 second clips so that they're the same as all of the other clips. And we can simply do that by clicking on the 3 dots next to a sample and clicking split sample. And then it will bring up this really awesome page where what you can do is you can kind of, you can pick how long the segment lengths are. But again, it auto-populates to 1,000 milliseconds or 1 second because that's what all the other noise samples are because it's smart, and it's a really nice feature of Edge Impulse. And what you can do is you can see like this one sort of is missing the sample, and you can click on these windows and drag them around, and you can click on the top left to like add another segment, and then click on the screen to add another thing if you want to split it into more segments. And then once you click on a sample, you can you'll get the ability to click play down here and listen to just what that 1 second is. And so you can make sure you grab the actual audio of what you're saying. So this is also a note to self. If you do the 10-second recording, you should make sure to leave a little bit of space in between. So you shouldn't do yes, 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 or you won't be able to split them nicely. You might want to do like yes, yes, or something where there's enough of a pause that you can actually add these individual segments in there. And then you just click split on the bottom right, and it will split the 10-second one into 5 1-second ones. And so all we're going to do now, and I'm going to pause again, but I'm just going to pause again here. But what I was going to say is just go and record some audio. Do 2 keywords, get 30 samples minimum. 50 would be better. And it says here we'll resume in 10 minutes, but I'll leave it up to Marco and Marcelo and whoever's running the show right now to figure out that exact timing. But I'm just going to pause here again for questions as well. So again, I'm going to start up again, but I assume you can, pause the video in case you still are recording data, which if you just are playing this through in real time, you should still be recording some data. Yeah. And so once we're done, we'll need to perform that train test split, which again, you can get to by clicking on dashboard and scrolling all the way to the bottom. Or if you're in this thing here, you'll see there's this little like triangle of like warning. And if you click on that, that'll pull up a thing that'll allow you to do your training and test split. I've found that when we're using this pre-populated large data set, and then you're only adding like 30 to 50 samples of each of your words, the automatic splitting sometimes fails and it doesn't do it correctly. So you'll see this says 80-20, but when I click on it, or when you hover over it, you'll see 1 or more labels in your data set has a poor split. And if you click on it, what you'll see is that the automatic split for some reason worked great for noise and unknown, and yes, but it didn't work for no this time when I ran it. I don't know why it didn't work really well this time, but what you can do is you can just go manually and click on the 3 little dots and move to test set a couple of them individually. And I would suggest not moving like 5 in a row, but like skipping around a little bit, because the ones that are right next to each other are from that same recording, and it would be better if you did more random to move it to your test set. Equivalently, by the way, I've had it sometimes where when I've done the automatic thing, it moved all of no into test. And so I had to move some of them back into training. So you should just check and make sure by clicking on that little, that symbol here, which will change into not being a warning, but being a happy symbol. If it's doing well, you should just look and manually inspect and make sure that all of your classes are nicely distributed between your different things. And what you want is something that looks like this, Although this run actually, where I only had about 30 seconds for yes and no, 30 samples, did not work very well. I did another one with 50 and it worked a lot better, which is why I was saying, yeah, 30 might work, but 50 will probably be better. So hopefully that gets you through collecting your data set and then setting it up into training and test data. What we're going to do next is we're going to talk about data pre-processing, a little bit of theory, and then like actually go through and doing it for keyword spotting, and then we'll deploy our models. And that will be the lab for today. So Marcelo and Sean actually talked a bit about why you might want to pre-process data a couple of days ago. So I won't sort of belabor the point, but I will point out that sometimes the signal that you get in is not particularly descriptive. And if you pre-process it in some way, you can give more information to the computer that makes it easier for it to tell things apart. So when we get these raw audio signals, it's a one-dimensional thing that has some blips as you're going along. It's time versus amplitude of the signal is generally what you're sort of plotting here. And this is some fine one-dimensional data. But it turns out that if I manually record yes quite loudly and no quite loudly, and I just look at this image, they look very similar. Now, these are different waveforms. I can tell that they're slightly different, but they look very, very similar. And I can imagine that it might be hard for the computer to figure out how to tell these apart. And so what you can do is, again, we're going to do the same thing you sort of did with the anomaly detection data. We're going to use a fast Fourier transform and decompose the signal into its frequencies. And really what's going on here is that any signal, like this signal on the right, or your really complex signal we have for yes or no, is made up of some combination of different sine waves at different frequencies. So for example, if you take these two sine waves and you add them up, you get this sort of wave on the right. And if you add enough different amounts of different frequencies, you can get sort of anything. And so what the fast Fourier transform is doing is it's figuring out which components of which frequencies roughly add up to become your signal. And so we're extracting a new level of information out of this signal. It's not just the amplitude over time. We're going to get the frequency distribution in the signal as well. And so that's what the fast Fourier transform is. We take the signal that used to be time by amplitude and we get frequency by amplitude. So we see, the peaks here are like which signals are the most of in this plot of our little signal here. And so we can get the FFT on the left of our signal that was this loud no on the right. But again, the FFT is just this two-dimensional thing. It's just frequency versus amplitude. Whereas on the right, we had time versus amplitude. We haven't really necessarily gained too much. And so what we actually do for pre-processing in audio, what is sort of considered standard, is to take the fast Fourier transform and build a spectrogram. And the way you do that is, again, just like as Sean and Marcelo were talking about 2 days ago, is you take multiple windows. We take multiple FFTs, and we sort of slide this window across and take the FFT, take the FFT, take the FFT, take the FFT, take all the FFTs, and then we sort of stack the results together. And so what you end up plotting here is frequency on one axis and time on the other axis, and then the color is the amplitude. And so what we've sort of recovered is a color image of this signal. Instead of just this one-dimensional thing, we now have like an image. And we're actually going to take this image and pass it through a convolutional neural network. And it turns out these images actually are quite nice, because when we look at the time series data, remember the yes and no loud looked very similar. And actually here I can plot yes and no quiet, and they also look quite similar. It's like loud ones are big, quiet ones are small. When I look at the spectrograms of these images, of these same exact audio signals, still isn't maybe totally clear to you at first, but if I highlight sort of this section of each of the spectrograms, what you'll notice is that in the yes, there's stuff there, and in the no, there isn't. And so there's like a clearly defined difference between these signals. There's a missing set of frequency bands that have any amplitude because of the way that I say the word yes and no. And so that's the sort of thing that now the computer can find and figure out. And that's why people use this approach to give more information to the computer to allow it to have an easier job at doing the machine learning tasks. And again, that's the only reason we ever do pre-processing, is we just try to make it easier for the computer. In theory, the neural network could learn all of this just from the raw audio, but in practice, this tends to work a lot better. So spectrogram is an image, we can use it in a CNN. Before we sort of move on and actually do this, though, it turns out that we can actually do better than a spectrogram. We can take some domain knowledge into account. And what that is that when humans speak and when humans listen, we only speak in certain frequencies, and our ear can only tell apart certain frequencies well. And so it turns out that, like, as you go to higher frequencies, you have a harder time as a human being telling them apart. And so what we can do is we can take the spectrogram and we can actually pass what's called the MEL filter banks over it, which sort of buckets things along that are really high frequency and leaves things sort of more separate as they are lower frequencies. That sort of mimics how the human ear actually can hear things. And what this does is it takes the spectrogram and it computes what's called an MFCC, which is now this more realistic processed spectrogram for human speech. And if you look at the MFCC versus the spectrogram, I think it's a bit clearer that there's a difference in this section, and you can sort of see a bit more clear, like the darks are more dark and the lights are more light, and it's really sort of brightened up this spectrogram and made it just an easier picture to tell the difference apart with. And that's why we use this in our projects. There's also a collab that allows you to walk through this and input your own audio from the edX course, and that's linked on the top right of this slide. And again, the PDF is already online, and the Google Slides, I think, also are. So you can go and click the link off the PDF. There is additional feature engineering we can do. Often these are sort of like good things to do, right? Remove noise, do all this sort of stuff. I actually don't want to spend a ton of time on this. I think we should just get to the hands-on part. But I will note that there's like lots of feature engineering you can do in general. And one of the big tricks in getting machine learning to work, especially on constrained devices, is thinking about how do you collect really good data and constrain your problem to something that isn't too complex, and how can you do good feature engineering to give something that is processed in a nice way to the simple model so that a small model can solve the problem. And yeah, this is a nice warning though. If you start doing crazy amounts of pre-processing in Python or in training, now the nice thing about Edge Impulse is it has, those blocks, and if you build a custom block, you have to give it a block for training and inference, I believe. But if you're just playing around on your own and you come up with this really amazing way to pre-process everything, like that's sort of the answer, and you do it in Python or in some other high-level language, you will need to write the C++ to deploy like onto the Arduino eventually. So often it's good to start with already created blocks or known things from particular fields that are known to be good. So that was pre-processing for keyword spotting. And now what I wanted to do is talk a little bit about how to actually do this with Edge Impulse. So what we're going to do is we're going to click the button here to create the impulse. And that's going to bring us back to a similar screen as we had yesterday. Now on the left, we have this sort of time series data thing, and you have the window size at 1,000 milliseconds. So that is, we have these 1,000 second clips. You have the window increase, which is sort of how fast is it stepping that over. The default there is 500. That might work quite well. I've sometimes decided to make that smaller, like move that down to say 200 milliseconds, which will cause everything to run a little bit slower, but that might create a more detailed spectrogram, might work well. You can play around with something like that. Leave the frequency at 16,000 hertz because that's what we recorded at. You then want to add a processing block, and we're going to add that MFCC processing block, which Edge Impulse already has built in here, and it includes that all the FFT, spectrogram, MFCC, all of that, and it produces the output as we'd expect. You'll note here, actually, the second one down is an MFE, and that's a different kind of MEL filter banked energy thing, but it's designed for non-voice audio. And so you can see now how, like, depending on the exact application, you can come up with more specific pre-processing that can help actually really tailor it to what you're doing. So we're doing speech today, so we're going to do MFCC, but if you go back and you want to do, I don't know, some sort of other noise, you might want to try the MF. Yeah, and so we'll keep it simple, we'll do that. But I leave this link here on the bottom. If you would like to add custom blocks, if you go to that link, it will walk you through how you can add your own custom blocks into Edge Impulse. And so you can do your own kind of custom pre-processing, whatever you want to do. And I also will note that you can use multiple blocks as well. You could do a bunch of different blocks in a row, custom, built-in, all these other sorts of things if you would like as well. You see on the bottom here, there's like add a processing block below the MFCC. You would just click that to add another one. But today we're just going to stick to the MFCC. We're going to keep it kind of simple. And you can also click then add a learning block. And we're just going to do classification with Keras because we're trying to classify into our two classes. So for me, it was just yes and no. We're not doing transfer learning because it turns out there aren't good sets of models pre-trained for speech out there and embedded into Edge Impulse. But that would be a cool research project. If any of you want to take that on, that would probably improve all of this a lot for everyone because we're going to train from scratch. Then you're going to click Save Impulse. So we've created it. We're now going to go to the MFCC and actually generate those features. Just like last time, I'm actually not going to change any of the defaults. There's actually a lot of information here. You can play around with all this sort of stuff, but I'm just going to click Generate Features on the top there and then click the green Generate Features, and it will run for a while. doing some work there because we actually have a lot of audio samples that it's going to process. And what you're going to get right is that feature explorer. And this is the latest model that I did for yes, no, using and their noise and unknown that I've given to you. And this one worked actually quite well on the hardware. And as you can see, it's actually visually quite separate. I liked this. You can click on it and sort of drag it around. And at first I was like, oh no, this is going to be bad. It didn't look that good. But when I turned it to this angle, I saw that the yes and no actually became sort of outliers, and the noise and the unknown were sort of more clumped in the middle. But it actually turns out that the unknown is sort of like around the noise in this particular thing. And so they actually are somewhat separate, but just not visually in a 3D sense, but in sort of like a spherical coordinate sense. I think they're actually pretty separate. And again, if your results aren't that different and clustered and they look very compressed, they still might work very well. It will often work better if you can visually see it apart, because that means in the beginning, the features are a little bit easier to separate. Like, you know, this would be perfect kind of separation. The thing I have here is not perfect, but it turns out it's kind of good, and it actually worked quite well. That's going to run for a little while. Yours might still be running. If you want, this might be actually a good moment to pause and see if there are any questions. And I apologize, these darn pads that help with reducing the echo don't stick to the walls very well. So next what we're going to do is we're going to click on the neural network classifier there, and we're actually going to go train our model. And I want to note here, since we're not doing transfer learning now, you can sort of put any model you want. There's a default model. I would suggest leaving it as is. It's worked quite well for me. But if you click here on the top of the screen, you can see there's these 3 dots on the neural network settings, and you can click switch to Keras expert mode if you would like. And essentially, in general, Edge Impulse has these pre-made neural network blocks that you can add. So there's this, you know, add an extra layer, and we can just click it and select convolutional layer and put that in, and it automatically, you know, takes care of it. If you go to expert mode, you can actually write your own TensorFlow code. So as you start to learn more about machine learning, if you want to do some things from scratch, you can just write the Python for TensorFlow right in here. That's all that's happening under the hood. And in fact, if you look at the particular model that's the default in here, on the left is the Edge Impulse blocks, on the right is the TensorFlow code. And you can see how they are very closely related, right? The reshape layer is model.add reshape, and it's 13 columns, and you see the number 13s in here. There's a 1D convolution and pooling layer, and it turns out you're adding a convolutional 1D and a max pooling 1D. And so it's all very related. And so as you start to learn more, if you feel more comfortable just writing it from scratch, you can write it from scratch. If you want to use the pre-existing blocks, you can use the pre-existing blocks. Just do be careful. While you could, in theory, add any code in here for training from TensorFlow, you need to make sure that the things that you're adding are supported by TensorFlow Lite Micro, or when you go to convert the model to a TensorFlow Lite Micro model later and actually deploy it on your hardware, it won't work. And so this link here is a good one to check out. It's the GitHub link to the all ops resolver for TensorFlow Lite Micro. And that's where they list all of the operations from TensorFlow that are currently supported by TensorFlow Lite Micro. And I know the team is trying to consistently grow this list. So over time, there may be more. But right now, that link will probably tell you exactly what new kinds of layers you can get away with using for training and actually get to deploy onto hardware. But yeah, for now, let's just stick with the defaults and click the green Start Training button and let that start training. And again, just like with the vision, you'll get your training accuracy and your validation accuracy. They'll probably start low, they'll go higher. Hopefully, they'll end up being pretty good. For me, on the one that I did most recently that worked quite well, I ended up with 96% accuracy. And if you looked into the accuracy breakdown here, now you'll see where this confusion matrix starts to become actually interesting and useful. Remember, again, along the diagonal are like the true negatives, true positives, or things where they actually predict, the model predicts what the label is. And off diagonal is where the model predicts something that is not the correct label. And if you sort of look at what I have here, it seems like no was always predicted correct. noise was 96.4% of the time correct, but sometimes it thought noise was unknown. Unknown was generally like unknown, but yes had this issue where when it predicted yes, sometimes it was unknown, and sometimes it was actually yes. It was only 80% of the time was it actually always correct. And so it seems like there's a little bit of confusion with yes and unknown, and maybe that means that I didn't enunciate my yeses enough, or maybe if I just put in more yes data, that will help with this accuracy. But these sorts of things will start to tell you and help you think about where you might want to add more data, what you might want to change in your model, right? Here, there's only one value that's not working great. So I would say maybe I should train more yeses. If everything was pure chaos, that might indicate to you that you might have more work to do at a fundamental level. But hopefully it came out pretty good. You can look at that feature explorer and you can look for the red ones, which are the incorrect ones. You can click on them and listen to ones and understand what was confusing. That'll show you the individual data points. And again, you have that expected runtime memory. Here, this model was tiny. It was expecting to only use 34K of flash and 5K of RAM. It will easily fit. We have no issues here. And the audio data we're buffering is much less than the visual data we were buffering before. So again, I think we're in much better shape fitting things. So that's designing and training our model. And so all we're going to do now is deploy it onto our Arduino. And we're going to do that the same as we did before. We're going to sort of skip all this auto-tuning stuff, but it's really amazing things that Edge Impulse has been working on. So I suggest you check it out at some point. But for now, we're just going to go to deployment. You're going to just click on that Arduino library and click build, and it will start to build you the Arduino library. Just like we did yesterday, we're going to do the quantized in 8 version, and that will get you the model you need for deployment. If you are on your phone and you would like to deploy it to your phone, if you go to devices, you can click up here, connect a new device, which will pull up that list of things you might want to add. And you can click show QR code to show that QR code again. And this time, instead of collect audio, you want to scroll down a little bit lower and click switch to classification mode. And that will build a project, and it will take a little while because it will compile. But what you'll get then is this thing that will start listening to you, and it will start streaming what it thinks the score is. So as you say yes, no, unknown, whatnot, you will see a score here from 0 to 1 for each of the no, noise, unknown, and yes, or whatever your keywords are, where it'll tell you what it thinks they are. And so you can play around with it right now on your phone and see how well of a job it's doing. If you, so zoom in there a little bit to make it easier. These are the confidence that the current sound is these various things. And the highest one's in bold, and the highest one will actually show up here. It'll say currently, I think this is an unknown word as you're talking to it. So this is how you can test it out on your phone. Just like yesterday, though, since we've built this Arduino library, if we're on Arduino, we're going to open up Arduino and add this zip library to our Arduino. Again, it's sketch, include library, add zip library, and then you'll find it in your downloads folder. And then we can go file examples, and whatever you called this project. For me, it was, the thing I cloned was SciTinyML 22 keyword spotting, and I just added test clone to it, and then it will add underscore inferencing. So you can go find that one, and we're going to open the Nano BLE 33 cents microphone example, because again, we're using the microphone. I suggest the microphone example over microphone continuous, because from my testing, I've been better at actually triggering it on the microphone one instead of the microphone continuous. The continuous one is constantly recording, but for some reason I can never say the word when the recording is happening, and it seems to just always fail for me. So I think the microphone one is a little bit easier. So I would suggest using that one, and we'll just deploy it. I don't expect you'll get any library errors, because I know you added the board files and all that other stuff last time, and there shouldn't be any libraries beyond the microphone, which is packaged, I believe, with the board files. And so it should just load and tell you it's done, and then we can open up the serial monitor. Of course, if you do get that error, right, where it builds correctly, but it says like device unsupported or can't find device, I would double tap reset to enter into bootloader mode, which should help with the upload. But once that's all uploaded, we're going to go to tools and then open up the serial monitor. And then you're going to start to see this coming through, and it's going to say, starting inference in 2 seconds, recording done. And it only records for about 1 second. So what I found is that if you are trying to say the words and you are getting a lot of noise and unknown, right? Like for example, this one, it thought it was for sure unknown, right? Its confidence was 89% this was unknown. But if you're saying yes, 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 no, 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 or whatever your word is, and you're constantly missing it, I would try to time this. And so this is how I've got this to work the best. So when it says starting inference in 2 seconds, I'm like 1, 2, yes. And usually then I'm saying the word yes right as recording is showing up on the screen. I'm not saying it after it shows up, I'm saying it like as it shows up. And when I time it like that and I get the timing right, I've had these models work very, very, very well. When I get the timing wrong, they don't seem to work. So I think it's a little bit sensitive to the timing. This is, of course, a test case demo setup. And if your model was really great, it would work really well in continuous mode, but you probably need a bit more data. Since we're training something from completely scratch with very, very little data, it's kind of miraculous that it works at all. So my suggestion would be to just like really work hard on the timing here and think about when starting inference shows up, like try to actually like say your keyword right as the like word recording ... is showing up on the screen. And if you time that correctly, it should work. I've gotten it to work, and I hope you can as well. And that would be, deploying keyword spotting onto your Arduino. So this might be a good moment to pause for questions if people had trouble with deployment, if people had trouble with their training failed or something like that. I'll pause talking for a second before I go to the summary. But I hope that you had some fun again with this lab and you got something working. Okay, so to do a quick summary of what we did today, now they've got time to play around with it and hopefully figure it all out. Right, today we did machine learning again. I'm just gonna keep bringing up the slide because I think it's important to remember, right? Like it's all about labeled data for supervised learning or good data for any sort of model training. To allow our computer to use a neural network to learn the mapping from inputs to outputs so that we can give it new inputs and it will give us new outputs. Again, we actually use convolutional neural networks under the hood. They're amazing for images, and we use them on pre-processed audio today, which we pre-processed into an image. And we sort of walked through that TinyML workflow. And so what we did is we collected data, but when we were collecting data, we were thinking about, or if we want to collect data really at scale for others and to deploy products, we need to think about who's using our model, where is the model used, why will the model be used, and why are you picking the specific features of your model, like the keywords that you're using. And then of course, we're splitting our data into training, validation, and test data so that we can have a robust way to train our model and test it. We then pre-processed data. We used FFTs and spectrograms to compute MFCCs, to get something that was really good for audio. Obviously, if you're using a different sensor, you might need different pre-processing. And pre-processing can be crucial to getting these simple TinyML models to work. But in general, there isn't one answer on what the right pre-processing is. It is the best thing to do if you're going to a new field with new sensors is to Google and try to figure out what experts in that field are using right now, even if they're not using machine learning. What are the kinds of things they're doing? Because those are the kinds of transformations you're probably going to want to use. We then designed we didn't really design a model. We used the convolutional neural network built in there, but we did pick a convolutional neural network because our input was this spectrogram picture. And then we trained a model and we got this output and we can analyze it through a confusion matrix. And then we used a quantized model again, and we talked a lot more about quantization yesterday, but I bring it back up again. It's very important in TinyML because it's one of the crucial ways that we can get our models to be small enough to fit on hardware. And finally, we deployed it onto our devices and then had some fun with it. So that's what we did today. So I'll leave you with one line, which is better data equals better models. The number one thing I would suggest if you want to improve your machine learning model is to collect more and better data. That is the most likely way to make things work. And so I really strongly suggest you think very carefully about what problem you want to solve and what kind of data you might need to do it, and collect that data and then train a simple model before you go down the rabbit hole of designing the optimal model architecture for your data. So yeah, that's it. That's all I have on data pre-processing for hands-on keyword spotting. I hope you enjoyed the lab. Again, I'm really sorry that I'm not live doing this, but I hope this worked out okay. And I hope I was able to maybe hop in on text or whatnot, but I will be on Discord and all those other things, and I'll try to join maybe later or tomorrow or whatever if I can get through all this chaos of this week. And I hope you all are having fun and enjoying the workshop. So thank you again and have a great day.